All right, so time to go over yesterday's homework on voltage and potential energy, electrical potential energy. So, first question, what do we have? We have a plus 5 microcoulomb charge is 1 meter from a minus 2 microcoulomb charge. What is the total voltage? 0.25 meters from the minus 2 microcoulomb charge, or 0.75 meters from the plus 5 microcoulomb charge. Okay, so basically we have this charge, and then a meter away is this charge, and we want to know what is the point that is 3/4 of the way from this charge, basically. So, how do we do this? We find the voltage from each of those two charges first, and then put them together. So, voltage 1 is going to be KQ1 divided by R1. So, this is going to be the plus 5 microcoulomb, so K is 9 times 10 to the 9, times Q, which is going to be 5 microcoulombs, divided by the distance. This is now 0.75 from the plus 5 charge. So divided by 0.75. So numerator becomes 45 times 10 to the 3, which in other words is just 4.5 times 10 to the 4, divided by 0.75, which is, I assume 60? Yeah, 60,000. 60,000 volts. Okay. So the second one now, AQ2 over R2. Now we're going to use the other charge. This is now the minus 2, right? Yeah. So minus 2 times 10 to the negative 6. Divided by now 0.25. So the numerator becomes negative 18 times 10 to the negative, or nope, times 10 to the positive 3. Which therefore becomes negative 1.8 times 10 to the 4, divided by 0.25. So, 72,000. And it's going to be negative 72,000 volts. Negative because of the negative charge. So what's the total voltage? Well, simple enough, just 60,000 plus negative 72,000. And you get a voltage of negative 12,000 volts. That's your answer. What would the potential energy be if a negative 3 microcoulomb charge was placed at this position? Okay, so now we're just using the fact that the electrical potential energy equals this new charge times your voltage. So the new charge is this negative 3 microcoulombs. And that's going to be times the negative 12,000 volts. So we have, again, it's negative, but we have negative times negative, so that's just going to be a positive, so don't have to worry about that. So times that, there you go, 0.036 joules. That's your potential energy. There you go. It's pretty straightforward, and you can see that, again, this is very, very similar to the whole electric field, electric force kind of calculation. The difference is that we don't have to worry about direction. Just positive, negative, add them together, boop, 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 there you go. Right? So you don't have to worry about direction. That makes things a lot easier. Okay. So now, let's move on to this question. 9-volt battery is 0.048 meters long. Assume all the charge at one end of the battery. What is the charge needed to produce 9 volts within the 0.048 meter long battery? Okay, so this is like the wrap-up question. We're solving for the charge when we know what the voltage and the distance is. Okay, so we have that. If you want, you can just sort of multiply things around. So if you multiply R on both sides, you have V times R equals KQ, right? And then if you want to solve for Q, you say Q equals VR divided by K, right? If you want to look at it that way and not just plug in numbers. So if you do this, You have Q equals the voltage, which was 9. Yep, 9 times the radius of 0.048 divided by constant. So 9 times 0.048, 0.432. Okay, so that's going to be now divided by 9 billion. That. I'm gonna divide by a couple more times just to get a 4. Oh god, 5, 6. This is not gonna work. Okay. Okay, that was that the crap? Let me just do it over. 0.432 divided by 9 billion. Okay. Okay, so it's 4.8. How many zeros is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Which means that's to the negative 11. Okay, yes, so this is 4.8 times 10 to the negative 11 coulombs. So again, that's a small amount of charge. So look, going back to what I said before about how, a coulomb is a lot of charge. For a battery to work, you don't need a lot of charge. So even these microcoulombs is actually kind of a lot. Okay, B was how many electrons are needed to get this voltage? Okay, so we have the charge that we need. So how many electrons is that when we know what the charge of one electron is? So all we have to do here is take that charge and divide it by the charge of one electron. Now you might think, well, wait a minute, but the charge of one electron is negative. That's true, and this has to do with something that we'll talk about later as to why the positives and negatives kind of don't really line up that great a lot of the time. That's going to come up for something, later. So just keep that in the back of your head, but you don't have to worry about it here. So, because again, you're not going to have like a negative number of electrons. This is going to be a number, so you don't have to worry about it. But you do have, okay, so this number divided by 1.6 and then divided by 10 to the negative 19. 300 million. Or that's 3 times 10 to the 8. Yeah, it's the speed of light. Nice coincidence. What would the potential energy be if of one electron experiencing 9 volts? Okay, so this is basically saying you have a voltage of 9, right? Oops. Right, you have your voltage is 9, and you put an electron into those 9 volts. So the charge, this new charge here, is the charge of an electron. Times 9. Now again, you might think, wait a minute, but this is a negative number. Again, yes, but remember what I said about how when you get a energy number, you should just kind of always have it be positive because negative joules doesn't really mean anything. So you just don't really need to worry about it. And so what is that times 9? Well, what's 1.6 times 9? 14.4. Okay, so this becomes 1.44 times 10 to the negative 18 joules. That's your energy there. Okay. Now D. How fast does the electron move with the release of this energy? Okay, so this is what I said at the very end of the question last time, where you can take this potential energy, and you can then say that is all changed into kinetic energy. So therefore, which is, again, 1/2 mv squared. So what this means is that you can take your 1.44 times 10 to the negative 18 joules and put that equal to kinetic energy, 1/2 times the mass of an electron, 9.11 times 10 to the negative 31, and solve for v, for your velocity. So, let's see, I'm going to get rid of the 1/2 and multiplying both sides by 2. So it'd be 2.88 times 10 to the negative 18 equals 9.11 times 10 to the negative 31 times v squared. So v squared is going to equal 2.88 times 10 to the negative 18 divided by 9.11 times 10 to the negative 31. And that is a number. Oh boy, okay. 2.88 times 10 to negative 18 divided by 9.11 and then divided by 10 to the negative 31. That number, oh boy. I'm just going to copy this number. Did it change the font on me? Did it change the font on me? No, I didn't. Interesting. Okay. So that's my number. Because what is it? It's 0.6. Okay, I'm going to round it, though, just to there. And then that's my square. So then I have to square root this. Is here. Square root. Okay. So this ends up being about 1,778,000. Yeah. About that. Wait, now give me for a second. Okay. This is my speed, therefore. So, what this means is, now this is a very simplified example, right? Because this all assume that the charge in a 9-volt battery is all concentrated on one end of the battery, which is not how it is, but that makes this an easier calculation to do. But at least gives you a sense of scale. So this means that when electrons leave a 9-volt battery to go through any sort of wire or circuitry or whatever, which we'll get into what happens when that happens later, they're moving at like 1,000,000 meters per second. Okay, so that's the point of this. And so this is also why this relates to, again, what I said a long time ago about how, again, 1 coulomb is a really big number. And so the question is like, why are we scaling it based off of that? It's related to do with this. So sure, if you have 1 electron, the charge that it gives you is really, really tiny, but that 1 electron is moving through your battery like millions of times a second. So that charge is therefore amplified like 1,000,000 times. So that's why this kind of, the scaling is weird. It's related to this. So anyway, this is sort of a peek into getting into circuit stuff, which we're going to get into either on Friday, maybe, or instead on just next week, Monday. I'm not sure exactly yet what I'm going to do with that. So, yeah. Okay. So, today, I just want to do some practice stuff here. And, I'm not even going to really worry about warm-up or wrap-up stuff, because I don't really know what to ask you besides just, like, doing more questions. So, instead, I'm just going to kind of give you a problem. And a problem that would normally, if you were solving for electric fields, would be really gross. But for voltage, it's not so bad. Okay? I mean, it's not great, but it's not terrible. So, here's the problem. I have 4 charges here. And I notice how they're all different distances away. So, how this scaling is that between these 2 large grid lines, the thicker grid lines, that's a meter. So, basically, I'm at a point here where I am half a meter from 1 charge, a whole meter from, this is 2 charges here, 2 charges, 1.5 meters from, this is 3 charges, and 2 meters from, this is 4 charges. Now, if I asked you to find the total electric field, you could do it. Okay, you could find, the field from this one, the field from that one, the field from that one, the field from that one. You would have the field from each of the 4 things, but then in terms of putting them together, you'd have to worry about direction, and that's when things get very complicated. Okay, especially once you take things out of just a straight line, then it gets a lot more complicated to figure it out, because then you have to do the thing with vectors, and you'll probably have to do like x components and y components, and the Pythagorean theorem, you'll have to mess with all that crap. And it's annoying, and you won't want to do it. But instead, what if I asked to instead just find the voltage? What is the voltage in this position? Now, you still have to start the same way. You have to find, what's the voltage caused by each one of these things at that distance? Let's do that first. we have, here's what numbers we have. Q1 is 1. And you know what? I'm going to keep the units there. Let's say nanocoulombs. Let's keep it the same for this. So plus 1. Q2 is plus 2 nanocoulombs. Q3 equals plus 3 nanocoulombs. And Q4 equals plus 4 nanocoulombs. Now my distances here, R1 is half a meter, R2 equals 1 meter, R3 equals 1.5 meters, and R4 equals 2 meters. Now, if I was doing electric field, I would have to clarify what the direction is, okay? So, for example, I have to clarify, oh, it's 0.5 meters, and also I'm down from this charge. This one, it's 1 meter to the right of this charge. This is 1.5 meters above this. You know, I'd have to do with that. But because voltage is not a vector, I don't have to worry about that. So, I don't have to deal with direction at all. So, the question is, find total voltage. Well, I need to find each of the individual voltages first. So, V1 is going to be KQ1 over click the thing, R1. Okay. So, 9 times 10 to the 9 times that first charge of just 1 times 10 to the negative 9, because it's a nanocoulomb, divided by distance of 0.5. Now this is actually very easy, because we have 10 to the 9 times 10 to the negative 9. So those just cancel. So we basically just have 9 divided by 0.5, because 9 times 1. So that's just 18 volts. V2. Now we have 2 times 10 to the negative 9 divided by, oh, now our distance is 1 meter. So we have 9 times 10 to the 9, 2 times 10 to the 9, so negative 9. So again, the negative 9, 9 cancels, so we have just 18 divided by 1, so we get 18 volts. V3, KQ3 over R3 equals 9 times 10 to 9 times 3, that's not a 3, 3 times 10 to the negative 9, divided by 1.5. So again, 10 to the 9, 10 to the negative 9, those cancel. 9 times 3 is 27, divided by 1.5. And you may not believe me, but what? Oh, because it equals the set of the second. There is 18 volts still. So you may see a pattern here. You can take a wild guess. So again, the exponents cancel. We have 36 divided by 2. That is 18 volts. So what is our total voltage? It is, actually, do I have a sigma thing here? I'm going to find the sigma. Okay, there it is, 228. There. Here's my sigma notation. It's the sum of the individual V's. That, oh my god. You know what? What was it? It was 237? No, it's 228. That was it. V, N. N is just saying, like, number. So there, it's the sum of the V's. So therefore, it is basically the sum of the 18s. So it's 18 plus 18 plus 18 plus 18 equals 72, I think. Yeah, okay. There you go. There's my answer. There's my total voltage. So yeah, that's a lot easier than finding the field. And we can double check this with this here. And this is not going to be exact because the numbers are not going to line up perfectly, probably. But yeah, that's pretty damn close to 72, right? So yeah, seems to line up pretty well. Now, one thing that you can actually do with this that's a little bit interesting is that I can, if I take this away, me take these two away also, is there. Now what I've done is I've changed it. So now instead of the only thing I did is I changed this to -1, and I changed this to -2. So if I did that, this would become minus, and this would become minus, which means this would become minus, and this is minus, which means minus, minus. So then, it doesn't become 72, it's now 0. And let's double check that. Yep, that's pretty damn close to 0. And you can imagine that for it to actually be 0, it'd have to be, a little bit more precise positioning of everything. But yeah, so that makes things pretty simple. And so this ratio of the fact that it's, I'm increasing, just going 1, 2, 3, 4, and this is also similar manner, 1/2, 2 halves, 3 halves, 4 halves, right? The fact that I'm doing that, they can end up just being the same number. Now, for the electric field, again, it's different because of the directions, but also just because of the r squared, that makes it so that this wouldn't line up this way that well, and you would get a grosser number anyway. So, yeah, this is a much easier example dealing with this with the voltage than it would be if it was with the electric field. So that is nice. I'm going to reset this back just because it's more interesting if you have it this way. Okay. Oh, because I had the plus. Okay. So yeah, that's definitely a much easier example in terms of getting that set up. Now, one thing that you could do, let's see. Let me do another kind of setup here. Let me reset everything. Okay, so I want all this back on. And let's have one charge there. Let's have 2 there. But then let's have 3 here. And the question is, what is the voltage here? Okay. Now, I know that's showing the field, but I want to know what is the voltage there. Okay. So again, the field, this would be a little bit tricky because you have to think about the direction from everything. But for the voltage, let's see how this wouldn't be too bad. So let me make sure this was 2. Yeah, that was 2. And this was 1. Yeah, okay. So let's check in the numbers with this one. So we have Q1 is +1 nanocoulombs. Q2 is now -2 nanocoulombs. And Q3 equals +3 nanocoulombs. I did +3, right? Yeah, okay. And then our distances here. So R1 is 0.5 meters. R2 is also 0.5 meters. It's just in the other direction, right? That's half a meter. That's half a meter. And then R3 is 1 meter. And the question is, find total voltage. So, from here, again, we got to find V1. Times 1 microcoulombs. Whoops, I did the wrong thing. Divided by 0.5. So this is actually the exact same setup as this first one up here. So that's going to be, again, 9, 10 to the 9 to -9. Those cancel, so we 9 divided by 0.5. So that's just going to be 18. Okay, that one's 18, but the next one should not be 18. So we have Q2 over R2. Now we have -2 times 10 to the -9 divided by 0.5. So now we have 9, again, 10 to 9, 10 to -9, those cancel. 9 times negative 2, so you have negative 18 divided by 0.5, so that gives you negative 36 volts. And V3 oops, wrong thing. Okay. Now we have 3 times 10 to the divided by 1. So we have, again, the exponents cancel, so we have 9 times 3 is 27 divided by 1, so we have 27 volts. So what is the total voltage? It's going to be the sum of the V's, which is 18 plus negative 36 plus 27, which equals 9? Yes. 9 volts. And we can double check that with this thing here. It's about 9, yeah. And it's off. Since I'm off just by a little bit, it's going to change my numbers pretty significantly, right? Because here it's 9.2. All the way, I immediately just jumped up to 11.7 just by that slight movement. So, yeah, makes sense. The number's going to be slightly off from how things works. So, anyway, you can see how that kind of works there, and it's definitely simpler to get than the electric field. It's again very similar, but it is a bit simpler because you don't have to worry about direction. And just because you don't have to worry about the r squared, it usually just makes the math a little bit easier. And so a last thing could be, a follow-up question to this would be, if you put yeah, sure, 0.5 nanocoulomb charge at this position, what will its potential energy be? And so potential energy, the key is you're taking this new charge, the 0.5 times 10 to the negative 9, and you're multiplying it by the voltage you just got, which was 9. So this ends up being, well, fairly simple to calculate. It's 4.5 times 10 to the negative 9 joules. So yeah, pretty simple pretty simple in that form there. Just like with the force, I really recommend that you don't just jump straight to the potential energy. Whenever you start solving for the potential energy, you should always find the total voltage first, and then get the potential energy from that. And always remember that, and I don't remember if I explicitly said this before when dealing with the force and the field, but for either situation, because again, for a thing like this, it's very easy to kind of get confused as to which charge does what. Right? So what charge am I using, for example? Let's go up to a question that was actually used up here. Yeah, so this question here, you have object A, B, and C. Which charge do I use where? How do I know what to do? Here's my main advice for any of this. You should never use the same charge more than once. Okay? So for this example here, we used QA to find the field, to find this field number, QB to find the field for this number, and then we used QC to get the force. Okay, we never used one more than once. So again, going back down here, now there's these 4 charges: the +1, the -2, the +3, and the 0.5, right? So notice I never use any of these charges more than once. So that's sort of the key for this, is that each charge only use once. So if you're ever sort of confused about when to use one charge over another, that's my best advice, is you should never use the same charge more than once, within a question, obviously. But yeah, so that's my main advice for that. So let's see how you are for putting all of this together. All of the field stuff, all the force stuff, all the voltage stuff, and all the potential energy stuff. All of that, see if you can put it together in the worksheet that I have assigned for you. Okay, now the worksheet's going to take some time to go through. So, I'm not going to have a video for you on Thursday. Okay, so I want you to spend the time, really spend the time, the effort to to try to get some answers for the worksheet. It's a lengthy worksheet, okay? So, see what you can do with it. I'll try to see if I can make it so the whole issue, people like requesting access, is not a thing. I'm gonna try to fix that. I'm new to at least putting assignments through Classroom in that sense, so that's why I was kind of iffy the first time. But yeah, so let's see how this goes. I will be going over it afterwards, but definitely Wednesday, Thursday, take your time and see if you can figure this stuff out. It is complicated, okay? I would say these concepts together maybe are probably like the hardest things that we do in the year, just because there is a lot to worry about here, and it's all very similar, which means it's very easy to confuse itself, right? It's very easy to mix things up and to get confused as to what is what. So keep that in mind. Do your best you can with the worksheet, and I'll see you back here on Friday. Okay. So, yeah. All right. I'm done.